Hello, I am Renzo Vargas, and today we will be presenting our research, Recurrent Neural Networks for Deception Detection in Videos. This is my partner Brian Rodriguez, and we did this research with the help of Willy Ugarte. Next. So we will be talking about the different parts of our paper, more importantly, the methods, and we will be discussing the results and saying some conclusions. The methods are basically the video structure and segmentation, the data transformation, the neural network application, and the proposed metrics. So, at in this day and age, determining if a person is telling the truth or not could be really important in certain situations. For example, in police investigations, if you know if someone is lying or not, it could have serious repercussions. So it is very important to know if a person is lying in those kinds of situations. However, humans don't have the ability to tell if someone is lying or not. It's very hard for them to know if someone is telling the truth. It's basically it's been proven that the chance of this happening is around 54%, which is basically chance. In the current methods for, or the most popular methods that exist today for seeing if someone is lying or not are the polygraph with the CQT method or the CIT method, which are just different questioning methods. Then the ERP and the fMRI. These methods have a success rate of around 80%, which is it's good, but specialists say it's not good enough for situations where knowing if a lie could be so important. So the downsides are basically that to know if someone is lying and you want to perform one of these tests on them, you would need to use specialized equipment and you would need a specialized agent to interpret the results, which is bad because this means that it's usually very expensive to do and not non-practical. Something bad also is that you need to read different biological signals, and these signals are not always indicators of if a person is lying or not, but indicators of if a person is nervous or different kinds of things. But they could also be altered, which leads us to our next downside, which is the that countermeasures exist. Some people know how to control their heart rate or different or their other different biological signals, and they can just counter the lie detection test. So we're going to propose an alternative that attacks these, especially the first problem, which is the expense, and is that we're going to use video, especially in our work we use the webcam, and we're going to use micro expressions to recognize if a person is telling the truth or not, using basically um, facial recognition and tracking these micro expressions, which are expressions that happen really fast in humans, and these usually happen when they face strong emotions, which could be a lie. And our contributions for these work is that we're going to be proving that the use of RNNs or recurrent neural networks are viable for the deception detection in videos using facial landmarks and micro expressions. Also, we're going to propose two new metrics to determine the precision of our deception classification, and finally, we're going to carry out an exhaustive comparison between different recurrent neural networks architectures on the topic by facial landmarks.
Uh, Now, my name is Brian Rodriguez, and I'm going to talk about the methods. First, we're going to talk about the video structure and segmentations. First of all, the process starts with a 30 to 40-second video of a person answering a question where the 68 facial point dataset that is shown on the picture below is applied while recording the data of each of those points moving through time. For example, there is a video of a person answering, and each of those points' location will be recorded and stored for further analysis. The data of this movement of the 68 facial points are detected according to the time window of the microexpressions. In theory, microexpressions are facial expressions that are so quick that they are undetectable to the human eye. They go as fast as half a second to even faster, that is 0.04 seconds. For this research, we decided to use a window of time of 0.05 seconds, that is equivalent to 1/20th of a second. But by having 30 to 40 seconds per video, there is a total of 600 to 800 moments in time or sequences where the exact position of the 68 facial points is stored and later normalized with a min-max scaler from 0 to 1. We use this scaler because it is sensitive to outliers. Now I'm going to talk about the data transformation. First of all, after we normalize the data, then it's transformed to 3 dimensions, because previously the 2 dimensions were the number of sequences recorded and the number of characteristics that we had. There are the 68 points and each of its coordinates, x and y, resulting in 136 characteristics. The third dimension that we add is the time steps, because they are added due to the use of the recurrent neural networks. The value of these time steps is 10 for all the evaluated models, since with other tested values there was not a significant change neither on the results of the models or the performance of each of the models. And all of the data used in this research for test, train, and validation belongs to the Miami University Deception Detection Database that we're going to talk further on the presentation. Now, we're going to talk about the neural networks application. By using multiple positions of those different points, it is possible to analyze their change in fractions of time undetectable to the human eyes, hence the microexpressions. Due to the nature of this input data that we're going to analyze, that movement on time and what that information provides, we decided to use recurrent neural networks. In this research, we use 3 different recurrent neural networks architectures, such as a long-short term memory or LSTM, gated recurrent unit or group, and the classical recurrent neural network or RNN. In addition, tests were carried out with the simple architecture, that is the classical cell of each of these 3 models, a bidirectional that allows to go through the future and the past in the context of the neural network, and the stacked version, that is 2 contiguous cells providing an even more profound detail on the neural network. And finally, we have our proposed metrics. First of all, to evaluate the performance of the 9 recurrent neural networks configuration models, we use the accuracy and area under the curve metrics to evaluate the performance of each of these networks. But not only we wanted to evaluate the performance of the models, we also want to evaluate the reliability of the prediction of each of the videos. That's why we propose 2 metrics that are complementary to each other: the average fidelity and the proportional fidelity. For the case of the average fidelity, each of the sequences, for example, 600 sequences, are predicted, either false or true. That means that on each moment of time, our model predicts if the user was telling the truth or not. To predict each of the sequences, there is a, a proportion of where, for example, in second 10, there is a 20% certainty that the user was telling the truth, where there is an 80% certainty of the user telling a lie. That's where the average fidelity comes in. We average all of those truth proportions and all of those lies proportions to determine the average fidelity for the truth and the average fidelity for deception, as shown on the formula to the left below. And for the proportional fidelity, like I said, there is a 20% chance taking the before example and an 80% chance of lie. That prediction for that moment of time is going to be that on that second the user was telling a lie because there is a higher certainty that the user was lying with 80%. And we use the number 0 to predict the lies and number 1 to predict truth. That's where we get the proportion of the proportional fidelity that we determine the total proportion of the general prediction of the video. Each of these metrics complement each other because one does not provide enough information of a prediction of a video without the other. They complement each other to give us a more detailed prediction of how it was determined.
Now I'll be explaining the results. Basically, for everything for these different architectures, we 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 trained them with three other variants. We used a single hidden layer, a bidirectional model, and also a stacked with two recurrent layers. Next slide, please. Out of these combinations, we obtained 9 different architectures, and we compared all of them. And among all of them, we compared the accuracy and the area under the curve, and the results were as shown. The best one was the GRU architecture with a 0.9369 for the accuracy and a 0.953 for the area under the curve, which was better than some other cases that we have been studying.
Uh, with the results, we try to test the quality of the predictions, as mentioned before. This is where we use our proposed metrics. On the left picture, we see the optimal values for detection. Using the average and proportional fidelity of the truth, the lowest values, that means the closest to 0% average fidelity or proportional fidelity, are the videos that are predicted with more certainty that are deceptions. For example, zero point 0.7 and zero point 0.6 are the closest to 0. That means that of all the 180 videos, those are the two that were predicted with more certainty that there were deceptions. But in contrast, we have zero point 0.4 and zero point 0.5 as labeled on picture, that those are closer to the middle of the scatter plot. That means with a 25 to 20% value, they are the videos that were predicted with less certainty to be deceptions. In contrast, we have the optimal values for truth. That means the value closer to 100% average fidelity and proportional fidelity are the ones that were predicted with more certainty to be truthful. For example, 0.1 and 0.2, they are the closest to 100 on each of these values each of these metrics. That means that both videos are the most certain predicted with truth videos. And in contrast, zero point 0.3, that is closer to 75%, that was the video with the least confidence of being predicted as truthful. Later on, we proceeded to analyze each of these 7 videos to the to find patterns that allow us to elaborate on which were the common factors of on these videos that could allow to de- to determine which are the patterns that made them the most general as a lie or as a truth. The conclusions of our research. First of all, we discovered through this research that using only recurrent neural networks is a viable method for lie detections. There are other methods that use convolutional neural networks, multiple layer perceptrons, or even a combination of convolutional and recurrent neural networks. But the use solely of recurrent neural networks was proven that is also an alternative using videos to detect the deceptions. The patterns that were discovered through the new proposed metrics, average fidelity and proportional fidelity, were, for example, that people who are closer to lying tend to speak with multiple sentences and short sentences in a short period of time. In contrast, the people that were closer to a more certainty of truth detection were able to describe the or answer the question asked to them with with more fluency and with less sentences, like they were telling us a history that they know by heart, for example. And finally, we could determine that a future research proposal could be the addition of this stacked group model to assembly models, or well, ensemble models, to provide relevant information and obtain possible results. Because there are multiple configurations that not only use video, but also use audio transcription and so on. So this could be an addition to this model to see how the result changed and if it can give a better result. That's all for our presentation and our research, but we also would like to express our deep gratitude to Professor Emily Page Lloyd, who enabled us to use the Miami University Deception Detection Database that was mentioned before, which made the results of this research possible. Uh, that will be all for today. Thank you for your time.